This is an example of a paired t-test, and the point of this is to illustrate the difference between when you deal with pairing and if you treat the data as unpaired. So what you have is members of a fencing club recording their weight before a competition and their weight after a competition. So any weight loss is assumed to be from dehydration. Why does paired test seem like it's going to be useful? Well, not all members lost weight, and is the weight loss significant? So let's look at part of the table of data. So there are 13 competitors, the weights before and the weight after. So competitor 1, 60 kilos before, 59.55 after, a difference of 0.45 kilos. There's some others at 0.45, there's some of 0. I think there's probably one within the data set that actually increases in weight. But if you go down and look at the average weight before, it's 59.92. So there's a reasonable amount of variation between the competitors. Now the weight afterwards is 59.62. So the difference between before and after is 0.3 kilos. But the difference between individuals, so the actual variability within the data set of weights, is about will be the square root of 1.51, which is going to be, well, it's going to be more than 1. So that's a problem. There's more variability in the weight between individuals than there is between those that have before, the weights before, and the weights afterwards. Looking at the box plot, the two overlap. There's no particular sign of any statistical difference. So let's do the unpaired t-test. Null hypothesis, there's no difference in mean weight. Alternative hypothesis is there is a difference between mean weights. The means and variances are in the table, so we can put those into the t-test formula. So the standard error for the difference is the variance of 1 divided by the number of the sample is 13, plus the variance of the other bit of after divided by 13, all square rooted, and it's 0.47035. So now what you're going to look at is what is the difference between before and after, the difference in the means, in terms of standard errors of the difference as a ratio. So the difference between the two is 59.92 minus 59.62, which is 0.3. So 0.3 divided by 0.47 happens to be 0.6378. So that is much less than 1. The variability in weights, on average weights between before and after, is less than 1 standard error of the mean. This is not significant. For a two-tailed t-test with a p-value of 0.05 as its threshold and 24 degrees of freedom, you'd have to have a t-test statistic of 2.064. And this value is a lot less than that. So there's no significant difference between the means before and after the competition. But if I'd have done the same analysis but pairing the data, so I'm taking into account the variation of between the individuals, so their weight before, and then I'm just calculating to the weight to afterwards on each individual. So null hypothesis is there's no difference in mean weight. Alternative is there is a difference between mean weight. In this case, the standard error of the difference depends on the standard deviation of the differences before and after. Now this is a very small number. The variance is 0.04583 kilograms squared. That's a lot smaller than the variation between the individuals. So the variation in differences, the standard error of the difference, ends up being the square root of 0.0484583 divided by 13. The calculated t-statistic is the mean of the differences divided by that standard error of the differences, which is 0.3 divided by 0.05938. In this case, the t-statistic turns out to be 5.05245 with 12 degrees of freedom, not the 24 you had before, because in this case, because of pairing, they're no longer independent of each other. So instead of having 26 data points, we now only have 13, which is reduced by 1 to 12 degrees of freedom. For a two-tailed test, p equals 0.5, the critical value, the ratio of the difference in terms of standard errors of the difference has to be above 2.179. In this case it's 5.05245. That means that there is a highly significant difference, and that the calculated p-value is going to be far below the threshold of p equals 0.05, and it's actually less than 0.001. So there's a highly significant difference in weight between before and after the competition. Now if I were to put that data into SPSS, this is the paired t-test table that I'd get out of SPSS. So you look at the data, you've got the mean difference is 0.3, the standard deviation is 0.21409, the standard error of the mean difference is that 0.05938, which we calculated. The confidence intervals for the difference are 0.17 to 0.43. The t-statistic is 5.052, which is what we got when we calculated it by hand. The degrees of freedom is 12, the 13 people being measured before and after minus 1 for the degrees of freedom, and the sig value is less than 0.0005, so it was recorded as 0 in SPSS. To calculate confidence intervals depend on the mean and the standard error, so you can calculate the confidence intervals for the difference is the mean difference plus or minus some t critical value depending on the level of confidence you want for your confidence interval times the standard error of the difference. But SPSS calculates it for you, so you don't need to do it. This is just for completeness, so you know how SPSS actually calculated it.